Hello everybody and welcome back to Calc 3 Online. So last time we talked, we kind of solved this part of the problem, and it's not too hard to show that this particle moving on this space curve and the particle moving on this one are not going to collide because they're not in the same spot at the same time, but they actually do cross paths. So at different times, they're in the same spot. And the way to show this is basically solve a system of two equations with two variables. So the idea is like if we take t1, let's say, which is maybe some time for r1 here, and I'm going to say, does that, can t1 equal 1 plus 2t2? So idea is like, can this x component align with this x component at different times, okay? Now that's two variables, so I need a second equation. So I would also need t1 squared to equal 1 plus 6t2, right? If I just take the second one there. And so now I should be able to solve for t1 and t2. I probably would take this and just do substitution. So 1 plus 2t2 times 1, whoops, that's not it. 1 plus 2t2 is 1 plus 2t2 squared. And then I would get on the left here 1 plus 4t2 plus 4t2 squared. And then I'm probably going to move, so those ones actually cancel. I'm going to move the 6 to the left and rearrange a little bit. And then I could divide by 2. And then I'm going to factor out t2 and set this equals 0. So we basically have that t2 can be either 0 or a half. And it's looking like if it's one of those, then they should intersect. So just to kind of show you, to be super clear, if t2 is 0, right, over here, that's going to happen when t1 is 1, okay? So this one happens when t1 is 1. If t2 is a half, that happens when t1 is 2, right? So if you plug in r1 of 1, you get 1, 1, 1. And if you plug in R2 of 0, you also get 1, 1, 1. So you can see that works. And then if you do R1 of 2, you would get 2, 4, 8. And then if you do R2 of 2, you get, that sounded wrong when I said it. This should be 1 half. Yeah. So if you plug in 1 half, you're going to get 2, 1 plus 3 is 4, and then 8. Good. So again, it works. So this basically just shows that, it passes through the space curve. If you plot this in Math 3D, if you plot this in Math 3D, at different times, they're in the same spot. Actually, at two different vectors are sort of shared by them. All right. So what I really want to talk about today is derivatives of vector-valued functions. And I'm going to start with this picture here. So derivatives of vector-valued functions really do kind of just work analogous to what you see in Calc 1. You still have this derivative definition, and I can actually draw it out and show you how this is working. So if you just do the vector subtraction here, r of t plus h, so t plus h, the idea is this is h units down the curve, we're going to be at a different vector here, right? And then if you subtract r of t, which is this one, then you should actually get this secant vector, right? And so like if I make this the yellow vector r of t, minus r of t is, I don't know, something like that. And so then if you go and do r of t plus h minus r of t, the resultant right here should be, this blue vector is supposed to be totally matched up with that blue secant vector. And the idea is as the h's get small, right, this dot, this was my plus h timestamp, like my further down the curve kind of idea. So as h gets smaller and smaller and smaller and smaller and smaller, right, this vector subtraction that I just did right here, and getting that, this blue vector is going to get closer and closer and closer until you get basically the, exact tangent line to the curve at a certain point, like P or something like that. So that's the idea, right? So really the same idea as derivatives in Calc 1. And probably the most useful place, and I feel like I broke a record with this in Calc 3, but it's just the way it is. The reason we take the derivatives of them a lot of times is really for the physical properties that kind of come out of it. So if you take, the first derivative, that physical property is just velocity, right? And then if you take its second derivative, that's acceleration. And so a lot of like physical science problems are basically modeling maybe like a position of some spaceship or something, and then you want to maybe you take the derivative and evaluate at a certain spot, and that'll tell you this green vector could represent the velocity of that spaceship or something at a certain time. And then if you take its second derivative, right, you get acceleration. And honestly, there are still things like jerk and all the other weird names that I can't remember off the top of my head right now. But these are the two big ones that we actually use the most often. So basically very similar to Calc 1. These physical properties still work. And I kind of just want to go through a few examples now and sort of show you how to use derivatives of vector-valued functions. All right. So this is like the classic Calc 1 tangent line derivative problem. So I give you a curve given by these parametric equations, vector-valued function here, and I want to know the tangent line to that curve at this point. All right, and then I'll talk about this in a bit. So we first have to figure out what time this point happens, okay? And the way I would do it is if you take the first part here, you know that 2 has to equal 1 plus t. So it's pretty quick to see that t has to be 1. You can double check them. If you put in 1 there, you get 1. If you put in 1 here, you get e minus 1, right? So everything is happening at time 1. That's just kind of an important little fact that we'll need here in a second. To do tangent line stuff, right, we're going to need to take a derivative. And the derivative really just works component-wise. So we're going to get derivative of 1 plus t is 1. Square root of t is going to be we'll do 1/2 t to the negative half. And then e to the t minus 1 will just be e to the t. Or e to the t minus t will be e to the t minus 1. So that's my derivative. And then the, kind of slope, I'm going to put this in quotes here, because it's kind of different. It's really the direction vector for vectors. But the direction vector is like the slope. So if I plug in my time where this is happening and get 1/2 e minus 1, that's sort of my direction. That really is my direction vector for the line. So I'll do d sub L. Then you have technically enough to write the answer really down. You have some variable vector equals a point, which we know is 2, 1, e minus 1. And then we're going to just scale this kind of slope vector or direction vector, which we just got using the derivative evaluated at a point, and that'd be it. I mean, technically I asked for parametric equations, but right, you can just pull out x, y, z if you want. So really, I'm just going to leave it like that. This is just something else I kind of want to talk about now. So sometimes you'll see capital T of t, and that is actually a very specific thing called the unit tangent vector. And the unit tangent vector is just taking the derivative and just basically making this thing length 1, making it a unit vector. So this is something that really isn't like super useful for this problem, but just so you see it now, because there are going to be some things later on where we need it. But if you take a derivative vector like this, right, and then you just normalize it, make it length 1 by dividing by its magnitude, that will give you a unit tangent vector. So like if I go to this picture, this vector might not be length 1, but if you divide by its magnitude, you get like maybe that vector, and now it's length 1. A lot of computers like things that are unit in length, so 1 unit long, and it just makes computations easier for them. So even though it might be more work up front, sometimes we do that to basically just make something a little easier in the long run. All right, so I just wanted to talk about some of these kind of derivative rules. So you see all these really in Calc 1, and honestly, they're not that different here. So if you take 2 vector valued functions and you want to take the derivative of that, you can literally just do the derivative of each. It's like it works that way. And scalars can be pulled out too. These actually have to do with the fact that the operator d/dt is linear. So in so our highest math class here at school is linear algebra, and being a linear operator is something you learn about in linear algebra. But you don't really need to know it right now. But these properties are basically what it means for something to be linear. And basically it works nice is really the idea. The rest of these here, so, well, no, not the rest, I guess. The next 3. So these are actually kind of like your product rule from Calc 1. So your product rule, actually, the order does matter, like in a lot of places, not necessarily in Calc 1 so much, but it's going to matter here. When you do the product rule, it's actually supposed to be the derivative of the first times the second plus derivative of the second, or well, the first times the derivative of the second. So basically the derivatives are on the ends like this, and that doesn't matter for a lot of things, but it actually would matter a lot for the cross product one, because it is like, the cross product is anti-commutative, so A cross B is negative B cross A. And so knowing the order of how the product rule works is actually really important. So even though some of these, like these ones, it won't really matter, it really will change it here. If you ever, and there definitely are going to be times where you need to take the derivative of a cross product, you really need to make sure you know that the derivative ones are on the outside. Derivatives on the outside. And this last one's just the chain rule, which is, there's really no weird things going on here. But if you have like a vector valued function of a function f of t or something, you would do like the derivative of the inside times the derivative of the vector valued function, just like that. So yeah, I mean, all these properties really just should look similar to stuff you learn in Calc 1. They're not really that different. I thought I would actually just show you this. This is, I actually pulled this from like an MIT open source kind of free Calc 3 page that they have. So that's me citing my sources. If you go through this, and you can pause the screen and really look through it if you want, but this actually proves the cross product rule with the derivative. for vector valued functions. So they basically just make arbitrary 3D vector valued functions. They compute the cross product. They take the derivative. There's a bunch of symbols that you have to bookkeep. Then if you end up looking at it, it has that structure of R1 prime cross R2 plus R1 cross R2 prime. But it really will work out specifically always with the derivatives on the end, like that. So that is actually something that I do need you to know, because really of this one, the cross product being anti-commutative, if you just had always had it in your head that you can put the derivative in the front, it really won't be wrong now because of that weird property with cross product. All right, I just wanted to do one more problem. It's just kind of a weird derivative concept-y question, but I think it's kind of a good one. So the idea is show that if for some constant c, just some number, the magnitude of a vector value function is always just constant. So it's always like 2 or something for all t. Then its derivative is going to be orthogonal or just perpendicular to r of t for all t. Can I move this? Yeah, I can kind of move that. All right, so basically this picture. So we want to show that a derivative, given this condition, this magnitude part, the derivative vector will always be perpendicular to the r of t, the original thing, okay? And so really the way we can do this is that we can just show r prime of t dotted with r of t would be 0. That's like what it means to be perpendicular, right? So basically you need to somehow get a dot product into the problem and then take a derivative of it, and you'll kind of arrive at that statement right there. So the way we can do that, we have this property, and I'm just going to kind of put it up here. So if you take the magnitude of a vector and square it, it's the vector dotted with itself. That's something that I proved like way early on with vectors. Basically, I'm going to use that. So I'm going to square c, okay? So I'm going to do c squared, which would be the magnitude of r squared, which would then be r dotted with r, right? Now, if I just take, basically take d dt of both sides, right? We know that the c is constant, so that's going to be 0. It's going to be 0. And then we're going to have d dt of r dot r, which would be, if you use like the properties over here, right? Specifically this one right here, I'm just going to, instead of u and v, I have r, 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 right? I would get r prime of t dotted with r of t plus r of t dotted with r prime of t. And so here the dot product is, the order really doesn't matter. It's not like that with the cross product, but with the dot product, it doesn't matter if you do a dot b or b dot a. They're the same thing. So really I have 2 of these r prime of t's dotted with r of t. Okay. And so we have 0 equals this. So then we can just divide by 2, right? So then 0 equals r prime of t, r prime of t dotted with r of t, which is exactly what I wanted to show. So we conclude that r prime is perpendicular to r for all t. Okay. I think the picture is actually good here too. So the idea is basically this problem has to do with like a sphere like this. So the only way the magnitude is going to be constant for all like t is basically if your curve lives on a sphere or something like that, right? Where it's equidistant. This sphere is all the points that are equidistant from the origin. And so I don't care where my vector goes. If I drew that vector out, to some r of, f. So if I have r of, t2 or something, some other vector over there, the behavior of the sphere, basically with like the tangent, right? We know that like you're going to get a perpendicular thing there. It's the same thing if you even went down a dimension, right? If you think of a circle and you like imagine a vector going out to the edge, then its tangent vector, that's where the name tangent with trig comes from, is going to be perpendicular like that. And you could do that anywhere on the sphere, you could do it anywhere on a circle, or you could do a hypersphere. It would be the same problem even if this was a 4-dimensional sphere or a 5-dimensional or 6-dimensional sphere. But yeah, that's kind of a neat problem, I think, and it's kind of a good one to know. It also reviews a really, really important thing that we talked about early on.